Chapter 26, Physics Theory Video 6. Now we are going to look at everyday examples of electromagnetic induction. Now we know that EMF is generated as a result of the movement of a conductor in a magnetic field. Now if we if we explain using Faraday's and Lenz's laws, we can say that an EMF will be induced wherever there is a rate of change of magnetic flux linkage for a circuit or a device. So remember these as nouns rather than trying to understand the whole lot of it. Whenever there is a rate of change of magnetic flux linkage for a circuit or a device, there is an induced EMF. So now we are going to look at a generator and a transformer to find out how the EMF is generated. Now we can generate electricity by spinning a coil in a magnetic field. So this is something that you have learned in O levels, how this is done. So this is the reverse of an electric motor. So what we do is we spin a coil in a magnetic field, and that results in a electric current. So in electric motor, what happens is, using electricity, we send electric current through a conductor in a magnetic field, and that results in a force, right? So here what we are doing is we are giving that force so that we rotate it, so as a result a current would be induced. So there are three different orientations here. As you can see, XY has changed the directions because it has spun around. When in the horizontal position, the rate of change of magnetic flux linkage is maximum. We get a large induced EMF because it is going through all of the magnetic field lines. When it is in a vertical position, magnetic flux is zero and the induced EMF is going to be zero. So for a rotating coil, so these are the situations, these are the four situations. For those five situations, for those five situations, this is what happens when the change in flux linkage and EMF, how EMF is generated. So this is drawn in either way, either direction in both of these situations. In the first one, they have drawn the flux linkage against the EMF. Then in the second one, again, flux linkage against time, and EMF maximum is reached at the tip of it. Then at the induced EMF against time, we can see the maximum EMF is reached at the point, at similar points. So this is the maximum EMF point. So at this point and at this point, it would have a maximum EMF. So if you look at the diagram, you will be able to see that when it is horizontal, you would have the maximum EMF. I hope that makes sense. So now we know that according to Faraday's and Lenz's laws, we know that induced EMF is equal to the negative gradient of the flux linkage against time graph, right? E equals negative delta in phi upon delta t. So this suggests that when the flux linking the coil is maximum, the rate of change of flux linkage is 0, therefore the induced EMF is 0. When the flux linking, when you have to remember from the beginning, you have to have that understanding. When the flux link in the coil is maximum, the rate of change of flux linkage is going to be 0, therefore the induced EMF is 0. When the rate of change of flux linkage is maximum, or when the graph is the steepest, induced EMF is also maximum. Right? So this is the word explanation of these two, in induced EMF and flux linkage. This is a very difficult lesson to understand, this part especially. If you don't understand, please let me know, then I will explain it more. Because this EMF has a varying, because it goes up and down, we know that the direction of the EMF is also continuing to change. So as a result, the current that is generated is also change in the direction. So we say that it is alternating current. In practice, what we do is, we have a large coil fixed, and we have a spinning electromagnet inside it. But in a bicycle generator, in a bicycle small generator, what happens is, the opposite of that is happening. There is a permanent magnet, that is made to spin inside a fixed coil. So this is how it is done. So just have a look at it. Look at how the iron core or the rotor wound in alternating directions. So the electromagnet poles are marked. So when that happens, what happens is, there is a current, a direct current is generated. Then transformers. We have discussed about transformers in O levels. So in a transformer, we have a primary coil and a secondary coil. They have a soft iron core, we call it the ring. When we produce an alternating current to the primary coil, that produces, there is a magnetic flux that is produced in this iron core. The secondary coil is again linked by the same changing magnetic flux. So it also has a soft iron core. There is an EMF induced at the end of the other coil. We can increase the induced EMF in the second coil by increasing the number of turns of the secondary coil. So if we have fewer coils, then it would have a reverse effect. That means the EMF would be lesser. So here what we do is, we input at this point, then we have another higher number of turns. So as a result, we will get a higher EMF. So you will have to do the rest of the questions, and then the summary is phi equals BA, then phi equals BA cos theta. That is also something you need to remember. Magnetic flux linkage, N, the number of turns into magnetic flux. They have both the same unit, Webers. One Weber is equal to 1 Tm squared. Then an EMF is induced wherever there is a change in the magnetic flux linkage. Then the Faraday's law gave us an equation without the sign, delta n phi divided by delta t. That is the rate of change of magnetic flux linkage. Then Lenz's law states that the induced current or the EMF is in the direction so as to produce effects that oppose the change that is producing it. So as a result, we get the equation for Lenz's law, that is the negative sign added to the Faraday's law equation. So negative delta n phi divided by delta t. So these are the details that we have learned. If you have any questions, please ask. If you do not have, do the last few questions and also the end of chapter questions. But before that, write down this note. Electromagnetic induction can be observed in everyday objects such as generators and transformers. In a generator, the opposite of an electric motor occurs. Where a rotation within brackets of force induces a current to flow through. So we rotate it by using hydroelectricity or diesel power, whatever. When in horizontal position, the magnetic flux linkage is at the highest. And in the vertical position, the EMF is 0. I would suggest that you draw this diagram along with these positions as well. Then you would be able to understand it better. Then write down. According to Faraday's and Lenz's laws, the induced EMF is equal to the minus the gradient of the flux linkage against time graph. Then write down transformers. In transformers, a primary coil and a secondary coil are wrapped around soft iron core. To the primary coil, an alternating current is provided, which results in a magnetic flux in the soft iron core. The changes in this magnetic flux induces an EMF in the secondary coil, which can be increased by increasing the number of turns of the coil. Right, so you know that transformers are used to transport electrical energy using overhead cables for long distance. The reason why we need To have transformers here and there is when it is when it is carried through a long distance, the EMF tend to reduce. So we have to increase it back again so that it would go through. So that is the reason why we have these transformers here and there. I hope you understood. If you have any questions, ask. If you don't understand, please ask. If you have understood, please do all of these questions.